Welcome back, everyone. I'm so glad you're here. And if this is your first time joining us in the Veterinary Epidemiology series, welcome. You're in exactly the right place. Today, we're diving into measures of disease frequency. We're talking about incidence, prevalence, and rates. And I want to be upfront with you. This is one of the most important modules in the entire series. I mean that. If you had only time to master one topic before your ACVPM exam, this would be a strong contender because these concepts are the backbone of almost everything else in epidemiology. Study design, outbreak investigation, surveillance, risk, all of it rests on a solid understanding of how we measure how much disease is out there. So over the next few minutes, we're going to build that foundation together step by step. We'll start from first principles, work through the math, look at real veterinary examples from dairy and feedlot settings, and I'll flag every major ACVPM exam tip as we go. We'll keep it conversational. This isn't a lecture. It's a study session between colleagues. So let's get started. Grab your notes, grab your coffee or tea, and let's go. But before we jump into formulas, let's ask the obvious question that doesn't always get asked. Why do we bother measuring disease frequency at all? If you're a clinician, you're already measuring disease in a sense. You're diagnosing animals, treating them, watching them recover or not. That's a clinical perspective. But the epidemiological perspective is fundamentally different. We're asking how much disease exists in a population, how fast is it spreading, and what does it tell us about risk control and resource allocation? Here's a practical illustration. Imagine you're a state veterinarian and you receive a report that 200 cattle in your region tested positive for bovine respiratory disease last month. Is that a lot? Is it a little? You genuinely cannot answer that question without knowing the size of the population being tested and over what time period. That's where our measures come in. Now, and this is critical, prevalence and incidence answer very different questions, and they have very different planning implications. Prevalence tells us the existing burden of disease at a given moment or period. It's most useful for planning services, estimating treatment needs, or describing the current state of a herd. Incidence, on the other hand, tells us the rate of new disease occurrence. It's your tool for understanding transmission dynamics, evaluating interventions, and conducting etiologic research. Confuse these two, and your public health or herd management decisions will be built on the wrong foundation. We're going to make sure that that doesn't happen. Now that we understand why these measures matter, let's start with prevalence. It's often the first measure students encounter, but it's also frequently misapplied. Prevalence. Let's nail this down right now, clearly and firmly. Prevalence is the proportion of a defined population that has the disease of interest at a specified time. Numerator, existing cases. Denominator, total population examined at that time, sick and healthy alike. No time period in the denominator. It's a proportion, not a rate. The formula, prevalence equals the number of existing cases divided by the total population examined times 100. Now, there are two flavors of prevalence you need to know cold for the ACVPM exam. Point prevalence is measured at a single point in time. Think of it as a snapshot. You test your entire dairy herd on Monday morning and 48 of 600 cows test positive for Johne's. Your point prevalence is 48 divided by 600 equals 8%. Clean, simple, one moment in time. Period prevalence captures all cases that existed at any point during a defined interval, say a quarter or a full year. The numerator includes animals that were cases at the start of the period, plus any new cases that developed during it. So period prevalence will always be equal to or greater than point prevalence for the same disease and population. When do you use each? Point prevalence is your go-to for cross-sectional surveillance, herd testing events, and regulatory testing programs. Period prevalence is useful when disease is episodic or you're retrospectively reviewing medical records over a calendar period. One common trap. Students sometimes put only new cases in the prevalence numerator. Don't. That's incidence. Prevalence captures existing disease, old and new. Here's an ACVPM exam tip. Prevalence equals existing cases divided by total population at a point in time. Incidence equals new cases divided by at-risk population over a time period. This distinction is the single most tested conceptual difference in the disease frequency domain. If an exam question gives you a snapshot of a herd on a specific date, that's a prevalence calculation. If the question describes animals being followed forward in time and developing new disease, that's incidence. Please don't mix these up. We've covered the snapshot prevalence. Now let's shift to incidence, and we'll start with its simplest form, cumulative incidence, also called risk. Cumulative incidence, sometimes called incidence proportion or simply risk, is the probability that a disease-free individual in a defined population will develop the disease during a specified time period. Let's unpack each piece of that definition because every word matters. Cumulative incidence, or risk, equals the number of new cases during the period divided by the number of individuals at risk at the beginning of the period. The numerator is new cases only, animals that were disease-free at the start and became cases during follow-up. An animal that was already sick when you started watching doesn't count. The denominator is the at-risk population at the start of the observation period. This is crucial. Animals that already have the disease or that are immune and therefore not at risk should be removed from the denominator before you calculate. Now, and this is the big structural requirement, cumulative incidence is only valid in a closed cohort. A closed cohort is one where no new animals enter after the study begins. Everyone starts together, everyone is followed for the same period, and losses are assumed to be negligible. In a closed feedlot pen where all calves were purchased together and no new animals were added, you have a closed cohort. In a flowing dairy herd with continuous animal turnover, you do not. We'll talk about what to do in that case in just a moment. Cumulative incidence produces a dimensionless proportion. It can be expressed as a percentage or a decimal probability. It answers the question, what was the risk of developing this disease over this period of time in this group? Here's an ACVPM exam tip. Cumulative incidence requires a closed cohort. No animals entering the population after the start of the observation period. If the question describes animals being added, removed, or dying of other causes in large numbers during follow-up, cumulative incidence is not the appropriate measure. Incidence rate, or incidence density, as it's also known, with an animal time denominator is required instead. Recognizing which measure is appropriate for a given scenario is a high-yield exam skill. What do we do when our cohort isn't closed, when animals are constantly moving in and out? That's where incidence rate comes in, and this is where many students hit a wall. Let's climb that wall together. Incidence rate, also called incidence density, solves the open cohort problem by using animal time in the denominator rather than a count of animals. This is a genuinely elegant solution once you understand the logic. The formula for incidence rate equals the number of new cases divided by the sum of time each animal was at risk across all animals. The unit of the denominator is animal time, animal days, animal months, or animal years, depending on the observation period. Each animal contributes time to the denominator from the moment it enters the population until the moment it either develops disease, leaves the population, or the study ends, whichever comes first. Once an animal becomes a case, it stops contributing time because it's no longer, quote, at risk. Let's make this concrete. Suppose you're monitoring a 1,000-cow dairy herd for subclinical mastitis over 90 days. Some cows leave because they're culled. Some develop mastitis partway through. Each cow contributes only the days she was healthy and in the herd. You add up all those cow days, and that's your denominator. The key conceptual distinction to carry forward. Cumulative incidence is a proportion. It's dimensionless and it represents a risk or probability. Incidence rate is a true rate. It has units, cases per animal year, for example, and it can theoretically exceed 1 if animals are at risk for a long time. They are not interchangeable. Rate gives us the instantaneous speed of disease occurrence. Risk gives us the cumulative probability over a fixed interval. Here's an ACVPM exam tip. Incidence rate requires an animal time denominator and is appropriate for open cohorts where animals enter and leave during follow-up. The denominator is not a count of animals. It is the sum of each individual animal's time at risk. Remember, incidence rate is a rate with units. Cumulative incidence, also known as risk, is a dimensionless proportion. Exam questions will test whether you can identify which measure to use based on the study design described. We've defined prevalence and both incidence measures separately. Now, let's connect them because in a stable population, they're linked by one beautifully simple relationship. Here's one of the most elegant ideas in all of epidemiology, and it's a guaranteed exam favorite. In a steady state population, one where things aren't wildly changing, prevalence is approximately incidence rate times average disease duration. P is roughly I times D. That's it. Think about what that's really saying. How much disease you see at any moment depends on two things: how fast new cases show up and how long each case sticks around. Turn up either dial and prevalence goes up. Let's make it concrete with subclinical mastitis. Say the incidence rate is 2 cases per cow per year, and the average case lasts about 45 days. That's 0.12 of a year. Multiply them. 2 times 0.12 gives you roughly 24% prevalence. And notice the real world herd prevalence runs 25 to 35%, so our simple model lands right in the ballpark. That's a nice gut check. Here's the part I really want to stick. Duration drives surprises. Johne's disease has a low incidence rate, but a very long duration, so it builds up to a high prevalence. Flip it around. Transient respiratory viruses have a high incidence rate, but a short duration, so prevalence stays low even though lots of animals get infected. High prevalence does not automatically mean lots of new disease. It can just mean disease that lingers. And this is why treatment matters in a way people don't always expect. If you shorten duration, better treatment, smarter culling, prevalence falls even if you never change the incidence rate at all. Johne's prevalence dropping after a better culling policy is the classic example. For the exam, know all 3 rearrangements cold. P is I times D. I is P over D, and D is P over I. They'll hand you two values and ask for the third, so practice solving in every direction. Time on who gets sick. Now let's turn to who dies and from what. Mortality measures are tested in both the disease frequency and surveillance domains, so let's get them straight. Mortality measures tell us about the lethal burden of disease, and there are a handful you need to know cold. The trick is that each one answers a slightly different question, and the exam loves to see whether you can keep them apart. Start with the crude mortality rate. This is all deaths from any cause divided by the population over time. Think deaths per 1,000 animals per year. It's your broadest signal. It tells you the overall death burden in a herd or system, but it won't tell you what's actually doing the killing. To answer that, you narrow the numerator. The cause-specific mortality rate keeps the whole population in the denominator, but counts only deaths from one disease, say BVDV deaths per 1,000 calves per year. That's what lets you isolate one pathogen's impact and decide where to aim your control efforts. Now, the proportionate mortality ratio is a different animal. It's deaths from one cause divided by total deaths, the share of all deaths that one disease accounts for. The beauty here is you don't need a population denominator at all, which is handy when you only have necropsy data. The catch: it can mislead you if the disease shifts overall survival in the herd, so read it carefully. Then there's case fatality rate, and this is the one people constantly confuse with mortality. Case fatality rate is deaths divided by diagnosed cases. It answers a very specific question. If an animal actually gets this disease, what's its chance of dying? It's about lethality in the sick, not death across the whole population. The HPAI example on the slide nails the distinction perfectly. Inside a hit commercial layer flock, the attack rate is basically 100%, and case fatality runs 90 to 100%. Devastating. But the mortality rate across all commercial flocks is far lower because most flocks were never exposed in the first place. So remember the takeaway. A disease can carry a 95% case fatality rate and still have a near zero population mortality rate if exposure is rare. Never treat those two numbers as the same thing. One last pairing. Morbidity versus mortality. Morbidity is the rate of illness. Mortality is the rate of death. You need both to see the full picture. High morbidity with low mortality points to something debilitating but survivable, like subclinical mastitis. Trap that catches people constantly, comparing two populations and forgetting they aren't built the same way. Let's talk about crude versus adjusted rates and the confounding problem underneath them. Picture two herds. Herd A has a 5% mastitis incidence. Herd B has 25%. At a glance, herd B looks 5 times worse. Clearly bad management, right? Not so fast. Herd A is all first lactation cows. Herd B is all fourth lactation and up cows. Older cows get more mastitis no matter how well you manage them. So is that gap about management or just about age structure? A crude rate genuinely cannot tell you. That's the whole problem with crude rates. They're easy to calculate, total cases over total animal time, one tidy number, but that single number hides the makeup of the population. Differences in age, breed, parity, or production stage get baked in and quietly distort the comparison. This is confounding in action. Parity is the confounder here. It's tied to both the exposure, your management practices, and the outcome, mastitis risk. Compare the crude rates and you've tangled management quality together with a demographic imbalance. You're not comparing apples to apples. The fix is adjustment, also called standardization, and there are two flavors. Direct standardization takes each group's age-specific rates and applies them to one shared standard population. That strips out the composition difference and gives you a standardized rate you can compare fairly. Indirect standardization works the other way. When you don't have stratum-specific rates, you apply standard rates to each group to get the events you'd expect. Then form the SMR, observed over expected. Read the SMR like this. Equal to 1 means observed matches expected, no excess risk. Above 1 means more events than expected, an elevated burden. Below 1 means fewer than expected, a protective pattern. And once you've adjusted, the standardized rate ratio finally isolates the management effect from the age effect. So the habit I want you to build for the exam and for real field work, before you ever compare two rates, ask whether the populations actually match on age, breed, and production system. If they don't, crude rates aren't comparable. You need adjusted rates or stratified analysis. Epidemiology has a wrinkle human epi mostly doesn't. We care about two population units at once. Let's unpack that and then layer in the outbreak measures that go with it. This slide captures something uniquely veterinary. We constantly juggle two levels of prevalence. We want to know how many individual animals are infected, and separately, how many herds are infected. Both matter and they tell very different stories. Within herd prevalence is the animal level, the proportion of individuals inside a herd that are affected. That's what drives clinical decisions: treatment load, culling, production impact. If 30% of a herd is seropositive for bovine leukemia virus, that shapes how you manage that specific herd. Herd level prevalence zooms out. It's the proportion of herds in a region that meets some infection threshold, often as simple as one positive cow by ELISA. On the slide, 15% of herds in the state are Johne's positive, 85% are free. That's the number that drives regional policy, trade restrictions, and eradication design. And notice the management logic flips with the level. A high within herd burden, say above 20%, calls for test and cull and a biosecurity overhaul, while a low burden under 5% means targeted testing and monitoring trends. Here's the key insight. A region can have low herd level prevalence, only a few herds affected, but very high within herd prevalence inside those few herds. Different lenses, different decisions. For eradication, you care how far it's spread across herds. For production medicine, you care how heavy it is within a herd. Same prevalence formula, you just redefine the unit. Now, the outbreak measures on the right. Attack rate is really just cumulative incidence during a defined outbreak. New cases over the at-risk exposed group times 100. It shines in foodborne investigations. Compare the attack rate in animals that ate the suspect feed against those that didn't, and that ratio points you toward the vehicle. Secondary attack rate measures contagiousness, spread to susceptible contacts after the index case shows up. The denominator is susceptible contacts only, and here's the single most common exam error. Do not put the index case in that denominator. The index case introduced the disease. SAR measures what happens next. The contrast on the slide says it all. FMD runs over 90% in naive cattle, wildly transmissible, while tetanus sits at 0% because it just doesn't pass animal to animal. A high SAR signals sustained spread. A low one points to a common source exposure instead. We've been measuring prevalence as if our tests were flawless, but they never are. Let's fix that because the number your test hands you usually isn't the truth. Here's a trap that catches even experienced people. When you screen a herd, the prevalence your test reports is the apparent prevalence, and it's almost never the true prevalence. Why? Because no test is perfect. Every test has some false positives and some false negatives baked in. And those errors push your numbers off the mark. Two test properties drive the whole thing. Sensitivity is how good the test is at catching truly diseased animals, the true positive rate. Specificity is how good it is at clearing truly healthy animals, the true negative rate. When either one slips below 100%, apparent and true prevalence drift apart. And the direction matters. A test with low specificity throws off false positives, so it overstates prevalence. A test with low sensitivity misses real cases, so it understates prevalence. That gap is widest when the disease is rare. When true prevalence is low, even a handful of false positives can swamp the real cases and make a disease look far more common than it is. The forward formula is on the slide. Apparent prevalence equals true prevalence times sensitivity plus 1 minus true prevalence times 1 minus specificity. Read it slowly. It's just real positives plus false positives. But here's the move that earns exam points, running it backwards to recover the truth. That's the Rogan-Gladen estimator. True prevalence equals apparent prevalence plus specificity minus 1 all over sensitivity plus specificity minus 1. Let's put numbers on it. Say a brucellosis ELISA has 95% sensitivity and 90% specificity, and your herd comes back 20% positive. Plug into the Rogan-Gladen. 0.2 plus 0.9 minus 1, which is 0.1, divided by 0.95 plus 0.9 minus 1, which is 0.85. That gives 0.118, about 11.8% true prevalence. Notice the test reported 20%, but the truth is closer to 12%. The imperfect specificity stacked the count with false positives. So whenever a question hands you apparent prevalence plus the test sensitivity and specificity, your job is to correct it. This matters most in surveillance for diseases like brucellosis or chronic wasting disease, where a wrong prevalence estimate carries real regulatory and trade consequences. Practice the Rogan-Gladen rearrangement until it's automatic. Estimate prevalence in a population. How many animals do you actually need to test? Let's turn that into a number you can defend. This is one of those topics where students either have it cold or freeze completely on exam day. Let's make sure you walk out with a clear framework because the logic is genuinely simple once you see the moving parts. Three things, and only three, drive the sample size for a prevalence survey. First, your expected prevalence, your best prior guess at how common the disease is. Second, your desired precision, how tight you need the estimate, the margin of error you're willing to live with, like plus or minus 5 percentage points. And third, your confidence level, usually 95%, which sets the z-score at 1.96. The formula ties them together. N equals z squared times p times 1 minus p, all divided by d squared. That's it. Z is your confidence, P is expected prevalence, and D is precision. Now, three insights that the exam loves. 1. Sample size is maximized when expected prevalence sits at 50%. That's where the outcome is most variable, so you need the most animals, which leads to the rule I want you to memorize. When you have no idea what prevalence to expect, use 50%. It's the conservative choice. It gives you the largest sample any prevalence could possibly require, so you can never end up underpowered. 2. Precision is expensive. Because d is squared in the denominator, if you cut your margin of error in half, you quadruple your sample size. That has real budget consequences in the field. 3. For a small finite herd, you apply a finite population correction that actually reduces the number you need. Let's work an example. Suppose you expect 20% prevalence and want to be within plus or minus 5 points at 95% confidence. Sample size is 1.96 squared, that's 3.8416 times zero point 0.2 times 0.8, which is 0.16, divided by 0.05 squared, which is 0.0025. Work it through and you get about 246 animals. Now watch what happens if you're uncertain and default to 50%. The same math with P at 0.5 gives roughly 385 animals, the maximum. That's exactly why 50% is the safe planning number when you're flying blind. So on exam day, spot the 3 inputs. Remember, sample size peaks at 50%, and remember, precision trades off as d squared. Get those and you can defend any sample size you propose. We've built up all these rates. Now let's talk about how we actually express them, because the denominator you choose makes or breaks interpretation. Let's talk denominators, because this is where a number either means something or means nothing. If I tell you there were 50 cases, your honest answer should be 50 out of what? 50 cases in 100 animals is a crisis. 50 in 10,000 is background noise. The denominator is what turns a raw count into a rate you can actually interpret and compare. The basic move is always count divided by denominator equals rate. The art is choosing the right denominator for the question you're asking. Most often in animal health, we use per animal rates, cases per animal per year, or cases per 100 animals per year. That's the workhorse for surveillance and research. But sometimes the animal isn't the right unit. For regional eradication programs, the herd is the unit. So we count per herd rates, something like 2.5 new BVDV positive herds per 100 herds per year. The epidemiological unit follows the decision you're trying to make. Dairy medicine adds a nice twist. Per lactation rates, like cases per 100 lactations. That matters because cows aren't always lactating, and when you're tracking intramammary infections, you want the denominator to reflect actual time at risk, not just calendar time. 2 practical habits to lock in. First, choose a multiplier that makes the number readable. There's no scientific difference between 0.0025 per animal year and 2.5 per 1,000. Pick whichever the listener can actually picture. Clarity is the only goal. Second, always state the time window. A rate with no period attached, per year, per 90 days, per lactation, is genuinely uninterpretable and can't be compared across studies. Never leave it off. Theory only sticks when you put numbers to it. Let's run 5 quick worked examples. Read each scenario, try it yourself if you can, and then we'll check the answers together. So this is the payoff slide. 5 worked cases that pull together everything from the module. Again, pause on each one if you want to attempt it before I give the answer. Case 1. BRD in a feedlot cohort. 400 steers, all BRD free at entry. 60 develop BRD within 45 days. Cumulative incidence is 60 over 400, which is 15%. Now notice the wrinkles. 12 animals were censored. They died before BRD. If you account for that, the adjusted CI is 60 over 388, about 15.5%. Closed cohort, fixed denominator, cumulative incidence is the right tool. Case 2, mastitis incidence rate. 120 cows, 15 new cases over 12 months, but 5 cows were sold mid-year, so each contributes only half a cow year. Animal time is 115 times 1 plus 5 times 0.5, which is 117.5 cow years. Incidence rate is 15 over 117.5, about 12.8 per 100 cow years. Animals leaving means open cohort, which means animal time. That's why we use a rate, not a proportion here. Case 3, HPAI, case fatality rate. A 5,000 bird turkey flock with confirmed H5N2. 4,700 die within 72 hours, 300 survive and are culled. CFR is 4,700 over 5,000, which is 94%. Lethality among diagnosed birds. Brutal, and a clean case fatality rate. Case 4. Yonis herd versus within herd prevalence. A state survey finds 180 of 500 herds with at least one ELISA positive cow, so herd prevalence is 36%. But within those positive herds, on average, only about 8% of cows are positive. Two genuinely different measures. Don't blur them. Case 5, secondary attack rate in an FMD outbreak. An index farm exposes 50 susceptible contacts across 3 neighboring farms, and 43 develop FMD within 1 incubation period. SAR is 43 over 50, which is 86%. Extremely high, exactly what you'd expect from how contagious FMD is. So the recap line at the bottom is your cheat sheet. Cumulative incidence is new over initial at risk. Incidence rate is new over animal time. Case fatality rate is deaths over diagnosed cases. Herd prevalence is not the same as within herd prevalence. And SAR is secondary cases over susceptible contacts. The exams want you to pick the right measure for this scenario, not just crunch the arithmetic. Every measure we built rests on 2 things, counting cases and defining who was at risk. Let's pull back the curtain on numerators, denominators, and where the data actually comes from. Every rate we've calculated today is only as trustworthy as 2 ingredients, the numerator and the denominator. This slide is about getting both of them right, plus where the raw data even comes from. Start with the numerator. Who counts as a case? This lives or dies on your case definition. A precise, consistent definition is the foundation of a valid measure. Make it vague, and the numerator swells or shrinks unpredictably from farm to farm, and suddenly your comparisons are meaningless. Case definition quality is numerator quality. Now the denominator. Who was actually at risk? That's everyone who could have gotten the disease during the observation window. And the discipline here is about exclusions. Animals that already have the disease, animals that are immune, animals never exposed to the risk factor, they don't belong in the denominator. Leave them in and you've biased it. So where does this information come from? On the numerator side, clinical and farm records, diagnostic lab submissions, slaughter inspection, serosurveys, and mandatory disease reports. On the denominator side, USDA NASS cattle inventory, NOMS survey data, farm and herd registration records, and DHIA milk recording organizations. Different sources, different strengths, and every source has its headaches. For numerators, passive surveillance underreports. You only capture the symptomatic animals that actually get presented. Case definitions drift between reporters, and subclinical disease is basically invisible unless you go looking with active surveillance or serosurveys. For denominators, the population never holds still. Births, deaths, sales, and purchases shift the at-risk count all through the window. Not everyone is equally at risk. In a passive systems, the denominator is often just an estimate, which brings us to the single most common epidemiology exam error, an inappropriate denominator. So drill these three questions every time. Is everyone in your denominator truly at risk? Have you pulled out the animals that already had the disease? Is the time period actually specified? Get the denominator wrong and you'll underestimate your rate every single time. On the math, now let's answer the so what? These measures only matter if they change what you actually do. Here's how they drive real decisions. This is where it all comes home. Frequency measures aren't an academic exercise. They're decision tools. Let me walk you through 6 ways you'll actually use them in practice. First, benchmarking. Put your herd's incidence rate next to published standards or peer herds. The National Dairy Mastitis Benchmark runs 25 to 40 cases per 100 cow years. If your herd's sitting at 80, that's not a shrug, that's an investigate immediately signal. Second, monitoring trends over time. Is your vaccination program actually cutting BRD? Calculate the incidence rate each year and plot it. The trend line tells you what casual observation never can. Third, evaluating interventions. Compare cumulative incidents before and after, say a new biosecurity program, but control for confounders like age structure, season, and herd size so you're measuring the program, not the noise around it. Fourth, prioritizing resources. You can't chase everything, so target the diseases with the highest population burden. High prevalence times high impact equals top priority. Numbers are what justify the budget. Fifth, supporting eradication programs. Track herd level prevalence across years. Falling prevalence validates that the program's working. Rising prevalence means it's time to reassess. Data drives the policy, not gut feel. And 6, maybe the most underrated, communicating risk to producers. Your herd has a 20% annual risk of a BVDV outbreak. Lands so much harder than BVDV is a problem. A quantified risk is what actually motivates someone to act. I love the line at the bottom of this slide. Epidemiology without frequency measures is like astronomy without a telescope. You can describe the sky, but you can't navigate by it. That's the whole point of today. We've covered a lot of ground together today. Let's bring it all home with a clean summary and the exam tips you need to carry forward. You made it, and I want to say genuinely, this material is hard and you put in the work today. So let's consolidate everything. Here are the non-negotiable takeaways from today. Prevalence measures existing disease burden at a point or period in time. It is a proportion, no time in the denominator. Cumulative incidence, or risk, measures new cases over a defined period in a closed cohort. It is a proportion and represents the probability of disease occurring. Incidence rate, also known as incidence density, uses an animal time denominator. It is a true rate with units. It is required for open cohorts. P approximates I times D. Prevalence, incidence, and disease duration are mathematically linked. High prevalence can mean high incidence, long duration, or both. Apparent versus true prevalence. Always adjust for test sensitivity and specificity when the diagnostic test is imperfect. Use the Rogan-Gladen estimator. Attack rate and SAR measure morbidity in outbreak settings. SAR measures within group transmissibility. PMR tells you the relative contribution of a cause within total deaths, useful when population denominators are unavailable. Herd level versus animal level prevalence. Always clarify your unit of analysis before interpreting or reporting. Sample size for prevalence studies is driven by expected prevalence, desired precision, and confidence level. Use 50% expected prevalence when uncertain. Here are ACVPM exam tips. Prevalence equal existing divided by total. Incidence equals new divided by at risk over time. Never confuse these. Closed cohort, use cumulative incidence. Open cohort, use incidence rate with animal time as the denominator. P approximates I times D. Practice solving for all three variables. Apparent prevalence equals the true positives times sensitivity plus 1 minus true positives times 1 minus specificity, rearranged to solve for true prevalence. Secondary attack rate denominator equals susceptible contacts only. Exclude the index case. PMR is a proportion of deaths, not a death rate. It requires no population denominator. Sample size is maximized at P equals 50%. Precision and sample size trade off as D squared. And that's our module on measures of disease frequency, from prevalence to incidence, from attack rates to the Rogan-Gladen correction. You've just covered some of the most foundational and most examined material in the entire ACVPM epidemiology domain. This is the stuff that separates candidates who understand epidemiology from candidates who have memorized it. I want you to truly understand it. My strong recommendation, don't just review these notes once. Come back to the worked examples, try them with different numbers, and quiz yourself on the conceptual distinctions, especially prevalence versus incidence and cumulative incidence versus incidence rate. Those distinctions will show up on your board exam. I can almost promise you that. If you found this module helpful, please share it with your colleagues who are also preparing for boards. This material is just as valuable for anyone in veterinary public health, production medicine, or regulatory work, whether or not they're sitting for the ACVPM exam right now. Follow us at Veterinary Epidemiology for new modules in this series, practice question sets, formula cheat sheets, and community discussion. Our next module will cover measures of association, relative risk, odds ratio, and attributable risk, and it builds directly on everything we did today. So make sure you have this module solid before you move on. Thank you so much for your time and your dedication to this work. It matters. You matter. Now go review these formulas, and I'll see you in the next module.